Good afternoon, everybody. I hate to be the one like right after your lunch. I know everybody's like a bit of a food coma, but we'll try to make it our best. So as from the introduction, my name is Luca, and in my day-to-day life, I work as an AI engineer. I was also a statistician or data scientist, now I turned into prompt maker, basically. And for the past couple of years, I don't know about yourself, but I feel kind of frustrated at times in prompting LLMs and understanding how they were doing the things they were doing. And in a way, we got into stuff like understanding how transformers work, and we've been doing a bunch of that in the past years as well. But it's been a couple of years since we started seeing really fancy papers from the latest AI labs talking about how we could try and explain the behaviors of such models. For instance, what follows here is one of the papers that came out right after it was given, like right before it was given a different version of this talk, ruining all the plan I had in mind. And this incredible paper by Anthropic is talking basically about how they were able to identify some subregions of the neural network of Claude models that were particularly active, and they could map to some areas of behavior that we were calling, they were associating to functional emotions, such as being afraid or being calm. So, for example, in this paper, Anthropic was claiming that they try to run Claude with the same prompt, only by varying the amount of milligrams of a certain drug that you can see here in graph brackets. And the more the amount of dosage of this drug it was increasing, the more they would find sort of activations of this drug. And they were associated with regions or emotion vectors they would post-hoc associate with being afraid, or on the other side, being depressed in the region that were supposed to be calm. And this sparks a bunch of questions, not rather about model consciousness and emotions themselves, but rather what do they mean with emotion vectors, activations. And around the same time, Ramp Labs, which is not an AI lab, but is actually a fintech company doing accounting, came up with a nice demo that's not active anymore about how you could basically have a model steer its behavior and generate, like on demand, change its persona without using any fine-tuning, without using any system prompt. And here, for example, I made this variation of a Gemma model behave a bit like a gym bro, and writing me a haiku, and in real time showcasing that you see here, life is all about life weights, bro, and no pain, and gains, etc., as you would expect from a character. And you can see from the right side that they could tell me that they were twisting some parts of the neural network that were associated with concepts such as the physique, the muscle, the proteins, the hypertrophy, and the gains, of course. So how do they achieve this? Well, they publish a blog explaining how this works, including a Twitter thread about how they did that. And the gist of this is that they run the model on prompts that invoke our concept, and they do the same for a neutral set, and they basically take the difference of this and find out this steering vector. And they also talk about residual stream. And all this kind of feels a bit like alchemy in a way. So today, I would love you to see how these people these researchers managed to bend the representation space and force a model to talk about these concepts on demand and intervene in them in such a way that's not through fine-tuning, not through prompting, but on a more intrinsic level by directly touching how the model weights, which are usually unchanged when we serve them. This field is called mechanistic interpretability, and its aim is basically to reverse engineer neural networks. This is a bit complex, and we will talk about it, but the idea is that this kind of represents a bit of a, well, paradigm shift, right? Because we're not talking about steering the model with please output some valid JSON, or please don't tell people how to write drugs, or we're not even training them to cover all of these edge cases, but rather move to feature level control, and we will make it clear what feature is by the end of this. And in this way, I would hope to explain it to you what is reverse engineering in the field of a neural network. So for the next 40 minutes, they will go on and about like this. First, we will give you a broad timeline and a bit of more of a context about where this research is going. And then we'll talk about the residual stream. This won't be math heavy. The next section won't be math heavy, but there will be a bit of jargon. And then we will talk about the residual stream and where do concepts and features live in a neural network. And this will be a bit more philosophical than that, and more mathy philosophical, if you will. But I think it will be, you'll be able to follow, because the math is not that hard, but mostly it's about how we can say where and what models learn. Finally, we talk about this idea that researchers in this field love talking about quantum mechanics as if this field wasn't interesting enough on its own, and we'll talk about superposition, but we won't be about cats. And then we'll talk about feature recovery and circuit tracing, which is the frontier of what's coming up. We will just briefly skim through that before going on to the takeaways. So it seems really packed. We will spend most of the time in the first 2 points. So by the time we finish talking about superposition, you will know it's over, and you can go back to your sleeping coma because of a lunch. Let's take a deep dive and go right in. Timelines. What are we talking about? What do we talk about when we talk about mechanistic interpretability, or mechinterp? Well, basically, it's a bunch of researchers that previously worked at OpenAI and moved all together to build Anthropic. I'm making an overbroad generalization of all this, but there is this circuit threads at Anthropic, which is hosted on their blog. It dates back to a distills.pub, which is a famous blog if you like the explanations about explainable AI and internal workings of machine learning models. They came up with this model, this visual language model in 2020 called about Inception Weave 1. And then when they were at Anthropic, they presented this paper called a mathematical framework for transformer circuits. And this was the stepping stone that led to all the research that I'm briefly skimming through in the next 30 minutes. The idea is that today we will be focusing on this yellow box about these toy models of superposition, scaling monosemanticity, and talk about Golden Gate Claude. Anyone here remembers that? Yeah, I see some people nodding. Okay, that's very good. So we will try to unbox that. And then we will just hint at what was coming after. And maybe now you're wondering why, right? Why we'll be talking about this. Well, the thing is that if you kind of squint a bit, you see that by the end of this, you will kind of realize that a lot of progress has been made in the past 5 years. And a lot of curious applications have sprung in the past year or so. And this feels incredibly promising and not only fascinating from an intellectual perspective, but also in terms of application that might be possible. So I think the sooner we talk about this, the better, because in the end, this might actually give us tools to diagnose and play with machine learning models, and especially large language models that are ubiquitous right now. We start with the residual stream, right? And with some figures that we might know already by a long shot. So the picture on the right is the transformer architecture with the encoder and decoder modules from the original transformer paper. And then on the left, we have a diagram made by Sebastian Raksha explaining the structure of Trinity Large, which is an open source large language model published by RCAI was it last year? It feels last year, but actually much sooner than that. They all have the same elements. They all have the multi-head attention layers. They all have the addition and normalization. Some do normalization before or after. Some do it both before and after. Some way they tell you how many layers there are, the length of whatever, etc., etc. But then there are some arrows, which are these ones, that we know nothing about. What are those? Well, it turns out these are residual connections. And they look like they're not important at all. And in a way, they might be, but if you're into mechanistic interpretability, that's the key concept. If you actually switch the perspective a bit, then we can start seeing that if we just switch the visualization and move the charts and the embed blocks on the other side, we see a highway that goes through from the embedding layer up to the very top. What is that? Well, this is what people have focused on Anthropic in this seminal paper, a framework for treating transformer circuits, is all about. The residual stream, this highway where basically meaning gets built. And if we go back here, we don't see that really well, but if we go below, we can see that the meaning in the embedding layer gets added and manipulated through each transformer block. Either the attention mechanism itself, which might be multi-headed. So for example, you see H0 to up to Hn is just the number of heads that the attention layer has. We will assume we just have one. And then the MLP layer, which is the feed-forward network, which might be an MLP, might be an MOE, if we're working with a mixture of experts. But the key intuition behind this is that all of these layers add up meaning and basically take what's at a certain point of this highway, transform it, and then throw it back. And they gave this intuition and this kind of explanation by which, well, maybe all of these transformer layers get the meaning, swap it a bit, do some fancy concept magic and arithmetics, and then throw it back into this highway, changing. And for example, what you can do is that if you have a certain representation coming at a certain point, then the attention layer can enhance that or even depress that. So in a way, that they kind of were thinking that maybe if there is a certain concept, say war, drugs, minorities or whatever, we could, if we find a way to tweak the layers, then we can, like, during training time, but also like at runtime, change those weights so that we can inject some new meaning at certain points of the neural network so that we can change what's actually working there in their internal representation states. So far, so good? Yeah, okay, I still see people nodding. That's very good. This is not the hard part. Let's talk a bit about math and technical concept and a bit of jargon. What do we talk when we talk about activation? Because here we're not really talking about weights anymore, but we're talking about the values that in real time get out of certain intermediate layers of the neural network. We call activation basically the amount y, or might be h, since it's a hidden state, but it doesn't really matter, which is basically the output of the matrix multiplication of the input of a certain layer times the weight. So if we have any sentence, any sequence of length t, and it gets turned into an embedding, then of course the activation at the layer at any layer inside the neural network will be just the output of that sentence that goes through the neural network up to that point, multiplied by the weight that it's going into, and then come out. So for example, if whenever we're talking here about activation, we're talking about, once again, the product wx plus bias, but let's just pretend we just have the w, okay? This is the weight, and the model parameters, the neurons, contain the weight. When we pass the input through the weights, we get the activations. And these are the internal states, the internal representation, and what what the researchers seek to change in real time when we talk about mechanistic interpretability. Let's just take a step back before going through all of this superpositioning, monosemanticity, and all the stuff thereof. And let's just assume for once that one neuron is just one concept. And if we have a sentence such as, I have a gray, and we make it, and we like spit it through a neural network for completion, and it spits out the word cat, in this ideal scenario whereby one neuron is just one concept, then we see that, for example, the neuron circled in purple fires. And when we mean fire, which means that the activation is, say, a positive value, 1. If that were the case, and the white neuron is like white, so 0, for example, inactive in the situation, we might be able to say, well, this neuron contains the concept of cat, because it fired whenever we wanted the word cat to be completed, or whenever the word cat came out of the LLM. And this is very good, and this entails like a really fancy, happy, nice property whereby, well, actually all the concepts are orthogonal in a way, because we have the concept of being a cat that's just completely orthogonal to the other one. There's no overlapping between the two vectors. They are separate on separate dimensions that do never cross each other. They don't have any, like the angle is 90 degrees, right? So they don't have any common component between each other. So they're clearly separated one from the other. And this is a really nice property from vector spaces if you're talking about linear algebra. But the truth is that life is not as nice as this assumption is. What actually happens most of the time is that neurons don't really just store one concept. And whenever we look at the activations given certain prompts, we see more than one neuron firing per layer. So at the layer level, we see more than one neuron with a positive activation, with a firing, or actually a negative one, but like a non-zero activation. And this means that actually our cat vector might be somewhere in a different position compared to where we expect it to be in this simple example where it just like orthogonal, that basically lies alongside the same axis we define as the x-axis in our case. And this means that whenever the neural network, we look into that and we see what's firing, we can't really say where the cat is. Maybe what fired could be something about like has whiskers. What fired could be something that, I don't know, means that it purrs. And what if we just have it like a different completion where instead of I have a gray cat, I own a gray hat. And then we see different activations. They are the same neurons. They fired, both of them fired, but they fired different like values. So what does this mean? Well, this means that this vector also contains the concept of the, I don't know, gray or wearable. This is the kind of challenge that the people at Anthropic back in 2022, 23, when they were reasoning about this concept that came out in the paper, were grappling with. So, and this is actually kind of trivial, if you will, because we can call it, and they used to call it superposition, but the idea is kind of trivial, right? If we have only neurons and one neuron learns one concept, then we will have to have incredibly large neural networks that won't be efficient to use. And in a way, we do not even know how to teach models certain concepts. They learn them through training. So we do not have any kind of control over what we teach a neural network. So, and even in retrospect, we do not even know what neural networks learn. And we can only make the assumption that basically features do not, and we cannot see empirically that features do not lie at the neural level, but in a more directional layer, whereby it's the weights of all the different neurons that fire, build up a vector, and that vector represents the concept we might be after. And this is actually, if you remember what Andrej Karpathy, like one of the former director of engineering, director of AI at Tesla, but also one of the founder of OpenAI, now working at Anthropic, was saying is that LLMs are basically a lossy representation of the word. So being lossy, they lose out on some meaning, but they need to compress all the knowledge in the data to build some compact internal representation of what's being fed into them. So if you will, it kind of makes sense that these models make the kind of lossy compression and give up on some meaning and are not completely like white box to us, if you look at those in this direction, because they might need, actually they need to do some deep learning or algebraic magic to compress meaning to be just more, to have more than one concept in one neuron, whatever the concept might be. So in the end, the direction that spits out being a cat here, the catness, might be a mixture of some weights that are expressed by the neurons themselves. So like a linear combination of all the weights, basically, right? And the direction of cat is no longer orthogonal with the other ones, but it will actually be a bit more of a result of some interference between different vectors. And how do we make this property like desirable? How do we make this work for us? And what the folks at Anthropic like reason about is that we can stuff concepts and features into vectors so long that they do not overlap too much. So long they are almost orthogonal in a way that we might have some more than one vector popping out alongside different dimensions, but they're still far apart. They can't be orthogonal. So the angle between those in any hyperplane might not be like orthogonal, so perpendicular. There might be some overlapping. There might be some interference between concepts, some of those concepts, but still they're still far apart enough that we can see this direction in the data. And this is what they call the interference or capacity trade-off, whereby we can increase the capacity of concepts that a model can store, either by increasing the amount of neurons that the model has, or by basically making it more capable of storing features. And we make this by, ideally they claim that the models do this, by reducing the space between vectors in this dimensional space, so giving up a bit of the quasi-orthogonality. This means that we increase the amount of interference, so basically the angle between the vectors decreases, so we can have more like overlapping in the same direction, but they're also able to store more concepts. And we see here interference. What's happening here is that the concept of cat spills a bit on hat and car, and it is in the proportion basically of the sine or the cosine of the angle between the cat vector and the car vector. And then what they mean is they also, if you think like if you add together the vector of hat and car, you might end up in the same place as a car or the cat. So we might have interference both in terms of components, but also in terms of addition, where some concepts play together and they can be confused. So there's a lot of things to understanding when we talk about like superposition, but the gist of it is that they theorized, hypothesized actually, I would say, that the models do not learn, like every neuron is not a concept. We see this pragmatically, like empirically, when we see and look through activations. And so maybe what's actually happening under the hood is that features and what's the models learn is learned through different dimensions, direction, vectors that are expressed by linear combination of the weights in each layer. And these, like the learning process makes some concepts spike out or be more clear if the learning procedure gives out some directions that are quasi-orthogonal. So in a way, we can shove more concepts into the model if we give up on the ability of clearly distinguishing them between others. And what they reason about and what they come after is that, well, maybe we can improve this trade-off, right, if we have more neurons, but this is not like a desirable property because we have incredibly large models that would be super expensive to run. They won't be able to run locally. They will be expensive. They will be slow. So maybe we can find something else. And what they try to, like, well, I wouldn't say postulate because it's not something like an assumption, but what they try to go towards is that, well, maybe if features are sparse, then we can make it clearer, we can make it simpler for the model to pick up those directions and avoid them being like overlapping with each other. And how do we do this? Of course, through data. If our data points, if the data that we feed the model through is homogeneous in a sense that every sample we send through the model in learning, so suppose we have like a model that talks about images, and every image is gray, the concept of being gray will be spread equally among all layers. Whereas will be learned like in this homogeneous, like noisy way, because the model like sees gray in every image, and other features will be picked up. On the other way, if we look at and we make some example, all the samples a bit more sparse, a bit more heterogeneous, then we will have like a data set of features, like just make it like pretend features that we think of when we design the data set to be more sparse, so we can have like a matrix where the concept of being gray, of being a cat, only lies somewhere, and not in every sample. And in this way, we make it easier for the model to learn sparse features. And in this way, the model can learn and build directions that are a bit more orthogonal, not really orthogonal, but quasi-orthogonal compared to each other, to minimize this effect of overlapping. Did I lost you here? Yeah, some people nodding with yes, kind of. Some people nodding with no, which is a good one. But I know like the theory behind this can be daunting. But the idea is, it's hard to reason about like vector spaces. But if you think that like an arrow points to a direction, what we are trying to build when we train a machine, like a large language model, is to build an internal representation of concepts, which it means arrows, basically learning the right ways to point like, the arrows in the right direction. And the process of learning, of training a neural network, means giving it a sufficiently heterogeneous data set that every part of a neural network, every neuron in every layer, can pick up the signal that comes from the images and learn to trigger when images of those kind go along, images or contents of those kind go along, and make this, and in order for this process to be like effective, if you want to explain where features live, we want that features and those data set to be sparse enough so that the features and the direction that are drawn when we look at the activation or the internal representation of those models are sufficiently far apart from each other, which means that we strive to have an angle that's as close as possible to 90 degrees between one of them. This is the mathematical thinking, but the idea is that the concepts are sufficiently far apart. And this is all on the empirical side. So what's happening, and we can call this over complete basis, but basically what ends up happening is that whenever we are actually observing an output such as cat, I have a gray cat and it's what is completed, what might actually be happening under the hood is that all of these neurons learn a whole lot more dimensions that there are neurons on that layer, and some of them are basically depressed or like cancelled. Some in the linear combination they're nullify themselves with each other, and only the cat concepts, all the features that allow us to identify a cat emerge. And this is like a really interesting it's the question that is entailed, which is what concepts are actually learned when we, through the training procedure. Maybe not really the concept of being a cat. We have no clear way of saying, do we learn cat? Do we learn having a tail? Do we have having whiskers? And this is actually, let me just take another like more food for thought thing, but the whole point of this field of research, which is mechanistic, is about isolating this feature, taking them out, and finding how these concepts actually live and how we can identify them in neural networks. We're getting past the mathy bits, but the idea is that, just to summarize this, they took all of these points and put them into a definition that is called the linear representation hypothesis. And the idea is that the neuron activation in the residual streams are a linear combination, so basically a summation, of different vectors. So basically when we build the concept of a cat, this is the result of weighing certain features, having a tail, having whiskers, being gray, purring, whatever. Or whenever we get the output, what's coming out of a neural network is basically a sum of the contribution, a weighted sum of the contribution of the features that the model has learned through the training. These features, they form this, what they call an over-complete basis, which means a basis of vector that do not have, that has more dimension than there are like in the space itself. So they learn many more features than there are neurons. That's the whole point. And this means that there will be interference, but if we make the training process good enough, diverse enough, the feature will be sparse. So they will be only located in certain areas. They will be spread apart in these different directions of the neurons. The interference will be sufficient for the model to pick up all of these features distinctively. And the good thing about all of this, and why I'm talking about this the whole this time, is that halfway through like 2024, Anthropic made it possible to verify this assumption, actually this hypothesis, and maybe turn it into a theory, in not only on toy models, but also on real models. And this is incredible because they scaled it to 1, 2, 3 layer depth, deep neural networks back to Sonnet 3.5, which is incredible because, of course, it has like hundreds of millions of parameters, if not billions. Actually, hundreds of billions of parameters, if not trillions. And what they need to do after, though, is to enable them to retrieve the features. So to say, hey, all these activation were firing, what concept do they represent? And this thing is called sparse dictionary learning, but basically the idea is that they went through in this 2024 paper is to explode the space of neurons way more, to have basically more neurons on the layer, and see, like through sparse activations, which regions fired. And then say, hey, this neuron that only these couple of neurons that fired, these ones are the neurons that contain the concept of being a cat. This is basically another paper that came out, and this is the last, not really the penultimate technical slide about this, but the idea is that they trained a different model that learned to mimic the activation given a certain input. And what we really need to think about when you look at this is that the original model, because they wanted to be efficient, want to be as small as possible to run faster, that has like a certain dimension. But what they can do is train another model that's way much larger in terms of the interdimension, and train it with a function, with a loss function that penalizes basically like the clipping, like the L1 loss, forces only some neurons to be active. And what they do basically is whenever they run an input through the first neural network, they take the Siamese one and then they throw the input through that one as well. And they see where the activation fire. Basically what I'm trying to say is that through the process of training another neural network that has the same depth but a different shape, which is much larger, they can try to find a way to bring us back to the ideal concept of having one neuron for one concept. So to disentangle all of this dimensionality of all the feature from all the overlapping dimension and just train a Siamese network, not really a Siamese one, but like a surrogate network, a replacement network that is sparse enough that we can use to train to basically distinguish all the concepts, disentangle all of them, if we will go on with the quantum mechanic talk and lingo. And this is where this brought us to Claude Code and the Golden Gate Claude. All of this was necessary to understand, and it was fairly technical, I know, to understand what was happening with Golden Gate Claude, which for those of you who do not know, dramatic pause, was a model or Claude variation of a Sonnet variation that whatever you ask them, they would answer about the Golden Gate. What's the best place in the world? The Golden Gate. Where should I be my fiance for a day? The Golden Gate. What's the best monument ever? The Golden Gate. What should be the 8th wonder, like what do they call it? The wonder, like whatever, that one? The Golden Gate, you know that. You could misspell that, it would say the Golden Gate. It's not like dumb that it answers Golden Gate to whatever, right? But whenever the question makes sense, and there is something with some affinity to the idea of a monument, of a romantic place, the Golden Gate would come up. And this seems like just playful at first, but if you think about it, they were able to isolate the concept of the Golden Gate inside the activation of Sonnet. What if that would be how to make drugs or to build to be something dangerous in the prompt? Like if you ask them, how do I bribe somebody? How do I build a bomb? Then you could be actively detecting that this model is firing some regions that are associated with something dangerous and depress them in a way so that the end user doesn't get what they ask for, in a way that's not simply just, please do not tell them how to make a bomb. Or something a bit more nuanced in a way that we do not have to train the model to do all of this kind of stuff with adversary examples. and we make the training model more effective. I mean, just hope that if we make them see enough examples of, hey, don't do this, do that, it will work. So this is incredibly powerful because if it's not a golden gate, it might be gender diversity, equity, right? Equality, inclusion, or whatever we care about. And what they do next, and this is a bit more of the speculative part of what's going on for like the past year, or maybe 2 or so, is that they were able to go through the individual layer and map the subnets that activate whenever we ask for a concept. So in these replacement networks, they're able to find all the dots that happen, all the dots that connect them whenever we ask for a certain sequence. So here, for example, let's assume that the sequence of token 1 to 4 is the capital of Texas is. They were able, whenever they see the output Austin, to trace back to the activations of all the previous inputs. And so they can able to build how these different features interact with each other, because here we have the concept of Texas, the concept of being a capital. Maybe we have the concept of the United States playing along. So they're scaling this way past the individual layer or individual token and being able to trace how these features interact with each other, way past the individual, like finding just one of them. And so what? The conclusion of these research is that they did find empirical evidence of what were the key assumptions of mechanistic interpretability. And they managed to hone feature recovery methods because of what they showcased was, I briefly explained actually, was just one of the methods. There are at least 2 more. One of those came out like 3 weeks ago or something, and I still need to read a bit about it. And they scaled that way past toy models up to old generation of feature or flag models from Anthropic. And it is incredible because now they're moving past identifying features, which has some liabilities, but still, like, let's just look at the good side for 1 second, to well beyond features and go to circuits, so mapping subregions and activation of the neural network. This still has some positive implications because they say that interpretability can become scalable, it can become casual, in a sense not it's like this casual, but like it has some causality into it. This is a bit of a really strong claim, but in a way this kind of helps us understand how stuff like mechanically works inside models. So this is not really like I'm teaching this concept to the model, but I'm not like just black boxing or observing stuff post hoc. And this is also, and this is, I think this is indisputable, it's becoming actionable. We saw it with the RAMP lab example. We can act on models, modifying actively their features, their activation, so that some concepts emerge more than others, or some other are depressed. And the goal of this, I didn't want to mention to skip this, but the idea is that interpretability is an engineering tool, something we may eventually be able to use to steer the models in real time, not just train and pray, but actually being active through the training and inference process to make the models say the stuff that we want it to say, or avoid it to say different stuff. And there are incredible applications that I've just like ran through and sped through, but these are safety, diagnostics, customization. I do not have to fine-tune a model to your memories or your contents or to your persona. I can just have it generate like a vector that represents you on the fly and customize my application for you. Maybe even in real time, in a way that's cheaper compared to just fine-tuning it, or just to shoving a huge prompt into it that you will pay for eventually. There are some limitations, of course, because this is mostly still a post-hoc process. The way we identify features inside these neural networks is just basically have an LLM speed through all the tokens that activated this region and say, hey, what this concept might be. And in a way, this is still largely subjective, and we do not know why some features do not fire. So I'm not saying this is a panacea, but after all, that this is like an active field of research that has been accelerating very much in the past couple of years. And this is why it should have like our full attention. And basically what we went through is that like an area of research was able to find empirical evidence of some key assumptions, such as superposition, and scale them from toy models to incredibly large state-of-the-art models in just a matter of 2 to 3 years. And we are actually starting to see applications of how to use this to identify functional emotions, for example, or other model steering in a way that will help us understand how some concepts are learned in neural networks or customize them and like on the fly. This was me. You see there's another person here that's not here, and Gabriele who helped me come through and read through all the literature and explain it to me, and it was super helpful. I'm really grateful for him to being able to sit down with me and talk about over sparse basis, or over complete vector basis. It was hard for me as well. But so if you want to talk about it, I would highly invite you to connect with me, or just to stop me after the session to talk about not only the math details, but that was me. Thank you very much.